All right, this is our second lesson in our polynomial review unit. So hopefully you've printed out these notes so that you can do that, or you're going to just take notes as we go. And so we're discussing polynomial functions, and we have this format that a polynomial function could be in. You say a sub n, meaning the first coefficient, x to the n power. So if this was to the fifth power, this would be a sub 5, the fifth degree coefficient, and the x to the fifth power, then this would be like the fourth degrees coefficient and x to the fourth power, etc. And it would do all that. So it's giving this kind of in a formula notation. A sub n, meaning this very first one, this term would be the highest degree, so therefore it's called the leading term, and a sub n is called the leading coefficient. Okay, so we always want to know that that very first coefficient in front, when it is written in descending order, that is the leading term, the whole thing, and the numeric in front of that is the leading coefficient. So here's some examples. This right here is a degree 0 because we would see this, we could see this as if it had x to the 0 power, which is just 4, so it is a degree 0. The leading coefficient, when I wrote it this way, you can see that 4 is a coefficient in front of x to the 0 power. So my leading coefficient, which is a constant, is 4. This here, the x has a degree of 1 because that's like an exponent of 1. So this is degree 1, and the leading coefficient is negative 5. This is a second degree, and the leading coefficient is 12. We have a third degree, and in front of the third degree expression, the third degree term, is a negative 1. This is a fourth degree, and the leading coefficient for that is negative 3. And this last one, our leading term, is 9x to the fifth. So this is a fifth degree and has a coefficient of 9. Okay, now we're going to look at parent functions of polynomials, so different types. So we're still looking at that 0 degree, kind of like up here, the 0 degree, the first degree, second degree, third degree. Well, when it's a 0 degree, that's called a constant function. An example of that would be f of x equals some constant, like 3 or 5 or 2. And so if I said right here is where my c is, then this is what a constant function looks like. It looks like a horizontal line. A linear function is a first degree. This is a, so I could write this as first degree. And I know you were dying to write y equals mx plus b, but that's not what we write here. This is a first degree polynomial. So we just say f of x equals x. There we have the parent function. This is the parent function of all linear equations. And that function looks like a diagonal right through the origin that is the perfect diagonal. It's a 45-degree angle. That is the parent function of all linear functions, well, first degree functions. This one is not, while this is linear, it's a constant function, hence it is has a 0 slope. It is a horizontal line. This is the parent of the linear function. For quadratic, the parent function is the function is a second degree equation, because remember this is second degree, and that parent function is the perfect, beautiful parabola that goes through the origin. And a cubic is a third degree, which is f of x equals x cubed. Again, we're writing parent functions, not just any cubic function, but the perfect parent function. And x cubed looks, sometimes we call it an S curve, looks like this, and that's what the parent function would look like. So these are parent functions of constant, linear, quadratic, and cubic. Then we do all sorts of transformations and changing them, but we'll deal with that later. Right now we just want to look at the parent functions. Okay, on the next page, there's a couple more of those parent functions. The quartic, which is fourth degree. So we've got f of x equals x to the fourth power, since that is a fourth degree. And a quartic function it also looks like a parabola. I want you to, when we just have, it's a little bit flattened parabola. It's a less bowl, a little bit flattened down here. After a while, when we have things happening, we transform this, it will give us a kind of a W shape like this, but that's only when we do things to the parent function. The parent function just looks like kind of like a parabola. And a quintic, the parent function, we've got f of x equals x to the fifth. Well, a quintic function looks like a narrower cubic function. It kind of flattens out a little bit in here as well. But it just does this, it doesn't start doing the loops that we normally see, because after we affect it, it could look like this. And that could look like what a fifth degree function starts looking like. But that isn't until, again, we do some transformations to the parent function. So it looks an awful lot like a cubic function. What we want to know about these polynomials, these different polynomials that we're talking about, the quadratic, the cubic, the quartic, the quintic, and the sixth degree and seventh degree functions, is the end behaviors. Now, when I say end behaviors, we're talking about this part of it here, just those end parts. And so that's the end behavior on that one. Here's the end behavior on this quintic, the end behavior. So here we have a fourth degree polynomial. And the fourth degree polynomial, well, it looks like the parent function. And it says as x approaches positive infinity. That means as we go farther and farther and farther to the right, this function is going higher and higher and higher. So the function is approaching positive infinity. For this function, as we look to the left, that's saying as x approaches negative infinity, meaning we're going this way, we look to see what's happening at the end behavior, and it's also going up forever and ever and ever, and so that is also going to positive infinity. Here we have an x squared function. This is a quadratic function, which is a parabola. But the leading coefficient is -1, which means it's going to take that parabola and turn it going down. So if we look at that, we can see that as x goes to infinity, so we're always looking at the right end behavior, this function is going down, so it's going down to negative infinity. And if we look on the left side as x approaches negative infinity, so we look on the left, the end behavior is that this also goes to negative infinity. Here we've got a cubic, and the leading coefficient is 2, so it doesn't change its behavior. And so we've got a cubic that looks something like this, and I'm saying, oh, on the right-hand side, as x approaches positive infinity, on the right-hand side, this is going up to positive infinity. But on the left-hand side, as x approaches negative infinity, we can see that it's pointing down, so it's going to go to negative infinity. This one is a cubic also, but this negative coefficient means that the function gets flipped over the x-axis, which means it kind of has this behavior. So we can see the end behavior. What's happening in here? Well, with this one, it's just a regular cubic, so it wouldn't do much of anything, but we're not interested in what's happening between the end behaviors, only on either side. So as x approaches infinity, that means on the right-hand side, this is pointing down, which is negative infinity, going down. And this one says as x approaches negative infinity, meaning look to the left, and this one's going up. So it goes to positive infinity, so it's your end behaviors. Here we've got another quadratic, so it's another parabola, but this parabola has a negative in front. So that means it is quadratic, which means the parabola is going to face downward. So when we look to the right-hand side, it's going to negative infinity. When we look to the left-hand side, it's also pointing down, so it's also negative infinity. Okay. Which just means it's going, you can't reach infinity. It's just saying going down, down, down forever. Here we've got a cubic. We've multiplied it by 1/2. I don't really, it's going to spread it out a little bit more, but the main thing is it's a positive, which means it does not change its end behavior. So on the right-hand side, it's going up, positive infinity, and on the left-hand side, it's going down, so negative infinity. And so there are some end behaviors. And I want to make sure I've been saying it all along, but when I say when x goes to positive infinity, it means the right-hand behavior. And when we say x approaches negative infinity, we're talking about the left-hand behavior. So we're looking at what's happening on the left. So the positive infinities look to the right, negative infinity is saying look to the left when we're saying as x is going those ways. So here's kind of let's look at what's happening here. When it's an even degree, so problem number 5 was an even degree. Problem number 2 was an even degree, and problem number 1 was an even degree. You'll notice in the even degrees, these always were the same. Positive infinity, negative infinity, negative infinity, negative infinity, negative infinity. So when it's an even degree, your end behaviors always match. But in an odd degree, the third degree, the third degree, the third degree, we don't have anything other than third degree here. But when it is an odd, the end behaviors are opposites. One's going to positive, the other's going to negative infinity. And it would change depending on the coefficient. So in an even degree, when it's a positive leading coefficient, the left-hand side is going up and the right-hand side is going up. And what's happening in between here, it doesn't really matter. Whether it's a fourth degree, fifth degree, it doesn't make any difference. But the end behaviors, they're both going up. When the leading coefficient is negative, again, since it's even, both of the end behaviors will point down. And then again, depending on what degree it is, this could be loopy-loopy-looping. So it's like there's a kind of a, you can't see what's going on in here. We're not interested in what's here. We're only interested in, not interested in this. Only interested in the end behaviors. When it's an odd degree and positive, well, like a cubic, the right-hand side's going up and the left-hand side is going down. What's happening in between to connect them? It doesn't make any difference. But my end behaviors, my right-hand side, so this is where x is approaching positive infinity, that the function is going up. And on this side, when x is approaching negative infinity, it's going down. When our leading coefficient is negative, it flips this. It flips it over to like the x-axis is what it does. And when that happens, the right-hand side, instead of going up, it's going to go down. And instead of going down, it's going to go up. And what's happening in between, we don't really care. But the end behavior is, as x approaches negative infinity, the function would be going up, 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 up. And as x approaches positive infinity, this function is going down towards negative infinity. Okay. So here it is, we're supposed to determine the sign of the leading coefficient. Both of these are pointing down, so I know that it is an even. So I'm going to have a negative number. So I'm going to say negative, like c, and then x to the 2n. It's going to be an even degree. So it's going to have some negative, and so I'll write it in words as well. We want a negative coefficient, and it's going to be even degree. Over here, well, this is the, when we look here, we're going, oh, it's this top one here. So the right-hand side's going up and the left-hand side's going down. So I know that this is going to be some positive coefficient, and my variable will have an odd power, and I can write that as 2n minus 1. That's how we kind of say odd numbers. So we'll write it in words as well. The leading coefficient will be positive, and it will be an odd degree. Okay? All right, let me get the next page of your notes. And this is where we're going to start talking about turning points, but also known as our vertices. So we're talking about this place right here and this place right here. They're called vertices, or they're also called our relative maximums or relative minimums. So if the turning point is higher than the nearby points, so if you look at this one here, this point that I just put here is higher than what's right next to it, so relatively close, and that's where the word comes from, relatively close to this point. Every point on this graph is below that point, and since that turning point is the highest compared to anything relative to it, we call this relative max or maximum. It's not the highest because I can see something over here is higher, but relatively close it is the maximum. We can also just say relative max, or L, we also write this as REL period MAX, relative max. If the turning point is lower than any nearby point, so here, this point is lower than anything real close to it. And since it's lower than everything real close to it, it is called a relative minimum, also known as a relative min, rel min like that. Maximum and minimums values can be called, there's a couple different things that they're called, and this is getting you ready for calculus, because in calculus we use this term all the time, and it's called an extrema. An extrema is what a relative and maximum is, that in this localized vicinity, this is the extreme value for it. And the height of it would be its, whatever this y value is, would be its extrema. And this one here, the maximum, the minimum here, it's the lowest value. And so whatever this y value is considered its extrema, because it is the extremely low. This is, and then we're always talking about the y values. The point itself can be called a vertex. So these are called vertices or vertex for one of them. It's also relative max and relative min, because then that tells you a little bit more about what's going on. The turning points define where the function is increasing or decreasing, because all the way up to that relative maximum, this function was going up. It doesn't matter if the arrow's pointing down. I'm talking about we're reading from left to right, and we're increasing, we're going up, 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 till we get to that maximum, that relative maximum. At that relative maximum, we turn to go down, and now it becomes a decreasing function until it gets to this minimum, and then it turns again to become a increasing function after that minimum, okay? So we want to find turning points on the function, and it says right here, using the calculator to do so. So you need to pause this video and grab your graphing calculator. So please pause the video, grab your graphing calculator, and then come on back. Okay, I have my graphing calculator here, and I'm sorry, I can't seem to get the camera to focus well on it because of the screen, but you should have your graphing calculator, and what we're going to be doing is we're going to be inputting this function into our equation editor. So we have our y equals screen, we hit the y equals button, and we're going to use it right here, and we're going to type in there x cubed. I know it's really blurry here, but this is what I'm typing. X cubed minus 6x squared plus 7x plus 2. And I hit enter. So it's in my calculator there. I kind of see less fuzzy there. And we're going to graph this. Right now, my calculator is, I just turned it on, and so I cleared it so that it's all in standard mode. But what I want you to do is make sure you hit zoom, and on the one that says zoom standard 6, that's where we should always start with. This is the typical -10 to +10, -10 to +10 window. It's not a square, it's not squared up, but it is the standard window, and then we would adjust our window if we couldn't see it very well. Well, we want to find the relative maximum minimums. We want to find this relative maximum right here. To do that, we're going to type on our calculator. First of all, we're going to hit, it says use the calc menu. So the calc menu is this blue up here. So I'm going to hit blue, second calc, And then on here it says maximum. So I want to hit the maximum, which it says maximum is number 4. So I just hit number 4. And now it's saying to the left, the bound on the left. So you're moving your cursor so that it is definitely to the left of that maximum, but kind of close, and hit enter. Then you go over to the other side to the right of it and hit enter. On my calculator, it gives me a little boundary. It says, oh, is this the area, the local area you're talking about? And the answer is yes. To guess means to move your cursor to about where you think it is and hit enter. And it's really blurry. I'm sorry. I can't. Your calculator should, I just can't get it to focus on it. But down on the bottom, sorry, down on the bottom, it's going to give you the X value for where that is, and the X value for where, and the Y value. It's going to give you the coordinate point. And my calculator is giving me 0.71, comma 4.30. And that is my relative maximum. We're going to go through that same process to find our relative minimum. So we're going to do blue, calc, minimum is 3. We're going to do move the cursor to the left side of it. Then we're going to move the cursor to the right side of it. Then we're going to try to move our cursor close to it, hit enter. And then it will tell us down the bottom our X and Y coordinates. And it's saying 3.29 and negative 4.30. Okay. So that's what I have here. Now I'm going to do a quick little sketch of what I've got here. See this, and it looks kind of like this. It looks like this. Okay. And so we found this coordinate point, and we found this coordinate point on our graph. We're now asked to find increasing intervals. On this graph, from forever down here all the way up, this is increasing. This is also, because it's going up forever, this is also increasing. So we're going to use interval notation. And the interval notation says from negative infinity all the way to this maximum X value, 0.71, it is increasing. Now, you can either put brackets or you can put parentheses for that, because I don't count it as increasing right there, but that's fine. The other interval of increase is from the minimum, 3.29, all the way to positive infinity. And usually we should put a little U symbol in between those, which means the union of. For the decreasing, well, it's only decreasing from this maximum down to this minimum. This right here is where it is decreasing. So I'm going to write that in red, in fact, just so we can see that easier. It's decreasing from the maximum of 0.71 all the way to the minimum, which is 3.29. Again, you're always writing the X values for an interval because that's about the inputs that we would use. For this problem, we're going to take this function, graph it, and then we're going to fill out all this information. I'd like you to pause it and try to do your best, because this is a review unit. Doesn't mean you remember everything, but you might remember some things. I'd like you to pause it, attempt to do this problem, and then when you come back, I'm going to have it done, and then we will discuss it. Okay. So hopefully you were able to do the graphing here. It said to use a table, so I have a table here, but when it says use a table, you're still also using your calculator. So I put it into my calculator and went to the table feature on my calculator. How did I do that? Well, I put in the equation editor, I put in the function, and then all I did was I went blue table, and there's the table there. You can cursor up and down the table, and I got my points. So I have my from -2 to +2, the different values that I wrote down my table right here, put those points on the graph, connected them, and again, you know, you could use your calculator to graph this. and double check that what you have in your graphing calculator is what you ended up here. The domain, meaning what numbers can you plug into that function? Well, all of them. There isn't a number that would cause any issues whatsoever. So therefore, my domain is all real numbers. This is a continuous function. It doesn't have any holes or jumps or anything weird happening. And it goes forever up and forever down, which means its range is all real numbers as well. The relative maximum, well, when I graphed it using the table, it looked like this, but I did look at my graphing calculator and I verified that that is the highest point. And I used the features like we did up here. So there's my relative maximum. There's only one of them. And my relative minimum is at 0, 0. The end behavior is on this one says on the right, it's going down, so it goes to negative infinity. On the left, it is going up, so it is end behavior is to go towards positive infinity. The intervals of increase between the minimum and the maximum, it is increasing. So from 0, from x equals 0 to x equals 2. That's not a point, that is an interval. So from this x value right here, where x is 0, all the way to where x is 2, meaning from this place right here, this is where it is increasing, it is going up. So that is the interval of increase. The interval of decrease is from negative infinity all the way to 0. So I'm actually thinking of from all of these negative inputs all the way to the input of 0, this function is decreasing. And from 2 all the way to positive infinity for x's, this function is going down, 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 down forever. Okay. We have our fourth and final page of notes for today. What I'd like you to do is the same thing we just did with the other problem. Now you have 3 more problems where you've got a function. You're to take the function, find a t-table, make the values, graph the function, find this information, and you're going to do it with each one. Make sure you're using a calculator to help you with this, and then you will have these problems, and then you'll come back to the video. So you're going to pause this, you'll come back to the video, and I will show you these 3 problems all the way done. So I will see you in a few moments. Make sure you've done the problem. Okay, so hopefully you have had time to both look at these without your graphing calculator and then putting them in your graphing calculator. If you're at home without a graphing calculator, there are things like Desmos, but it doesn't do as well with the relative max and min. It's a little bit easier. And I do want you to know how to use your graphing calculator. TI does have a site. I'm going to look it up and put it on the website. They've made available an online TI 83, something very similar to one of these, but online. And during this time of sheltering in place, Texas Instruments has made it available for free for students. So I will find that link. I've been hearing about this. So for this problem, you would have plugged this into your graphing calculator to look at, to find your value of for the graphing, and then you would have done your best to kind of estimate where those points are. Very challenging because these are, these decimals. You've got a relative minimum at negative 1.84. Well, on this graph, negative 1, negative 1.84. Well, it's like down here, negative 3.31. You can't get that accurate on this grid, but it did a pretty fair estimate of what that would look like. I kind of went a little bit over the line here as I was trying to go up it. So here it is. Pause the video and you can look at those answers to see what what I have written down here and check with your work. And you're getting all of this from your graphing calculator. I'm not asking you, there's no other way we're doing this at this point other than examining our graphing calculator. The second, actually it's problem number 3, is a 4th degree. So and it's a negative. So we know that it's going to be pointing downward before we even look at this. And when we examine it on our graphing calculator, we have this. So we have our end behaviors going down like we thought. The domain, you can plug anything you want in there. Your range, the highest point you have is right here. So your range is whatever, well, this relative max right here, the highest it was 6.50. So that's 6.5. Everything on this graph is below that, and that's what this is saying. That your outputs, your range, are all the real numbers that are below 6.5. And I could have that less than or equal to. If we wanted to, we could have an equal to. I hesitate getting too exact with that because it is a decimal approximation. So again, pause the video and you can check your numbers to what I have here. And the last one, this is a cubic. It's a cubic trinomial, since we're classifying things. And you can plug anything you want into it, and the domain is all real numbers. And you might notice right now that every single polynomial, the domain is all real numbers. That is one of the conditions of a polynomial, is that you can plug anything into it. There's no restrictions. So the domain for all polynomials is all real numbers. The range is different. When it's even, there's going to be only one part of the outputs that you're going to have below your relative maximum. I should say it's actually the absolute maximum. It's not just the relative. It's the highest point ever on this graph. Or it could be the lowest point, such as in this one. We have the lowest point, the absolute minimum, and my range is everything above that absolute minimum. But for an odd degree function, your range is all real numbers because it goes all the way from down negative infinity. It's continuous to going to positive infinity. There's no breaks or jumps in that graph. So here's the information. And that's the end of this lesson. And it's also going to be the end of, you fill this all out, that's going to be the end of your work for this Friday, because it's now going to be spring break, and I want you to have a nice relaxing time over spring break, finding things that you like to do, get caught up in any work that maybe you need to get caught up on, but also finding time to enjoy as much as you can, even though you are sheltered in place. So I'll see you again the week after spring break. We start back to school on Tuesday, not on Monday, but on Tuesday after spring break.